Welcome to this explainer. Today, we are genuinely tackling the architecture of everything. Seriously, we're looking at a framework so massive, so expansive, that it scales from the microscopic logic inside a language model all the way up to the macroscopic control of spacecraft re-entering the atmosphere. It's called the Frequency-Governed Self-Graph Reasoning Framework, or FGSGR for short. We're going to explore how this single, unified paradigm governs, well, literally everything in its domain, perfectly bridging the gap between abstract software reasoning and the very harsh physical realities of aerospace engineering. Let's get right into it.
Okay, here's our roadmap for today. We'll quickly hit the unverifiable prose problem, distilling thoughts into graphs, the irreducible error floor, inverting spatial perception, and finally, governing airspace in swarms. So we have to kick things off with the fundamental flaw of modern AI. Think about it. How do you actually verify the reasoning of a total black box that speaks to you in incredibly confident prose? It's a massive, massive challenge. Because when a highly capable language model solves a problem, its little internal errors are completely invisible. You don't see them until they surface in a perfectly fluent, beautifully written, yet confidently wrong final answer.
Which brings us to Section 1, the unverifiable prose problem, the illusion of confidence. See, because large language models spit out reasoning as giant blocks of text, you're kind of stuck. You basically have to either trust it wholesale or just toss it in the trash. There are three huge flaws here. First, uncalibrated confidence. The model's stated certainty is actually the least reliable right when it's making a mistake. Second is implicit structure. Circular arguments and double-counted evidence, they easily hide inside perfectly fluent paragraphs. You'd never know. And third, it's non-compositional. You can't just seamlessly merge two prose solutions together without asking the AI to completely start over from scratch. Its chain of thought is just a mess. It's unstructured and completely unauditable.
But what if we didn't just distill an AI's knowledge into a smaller model's weights? Because doing that just means the smaller model inherits all those hidden errors. Instead, the FGSGR framework takes a totally different approach. It converts that messy prose into an inspectable, typed, band-tagged knowledge graph. Imagine untangling a giant knot of yarn and laying it out perfectly straight. On this new graph substrate, confidence can actually be mathematically calibrated. Every single step can be governed, tracked, and audited. It's brilliant.
Moving on to Section 2, distilling thoughts into graphs, the FGSGR pipeline.
So how do we actually build this thing? It's a neat four-step process. First, a parser grabs that free-form AI reasoning and turns it into structured, schema-valid traces. Second, it distills those traces through a bridge to actually construct the graph. Third, it fuses multiple, totally independent reasoning traces together, basically letting them vote to boost the overall accuracy. And finally, step 4, it pierces the remaining error floor by bringing in formal mathematical verification. Now consider this concept of the lambda band, also known as FGSGR omega. This is essentially the math police of the system. By isolating the mathematically checkable steps into this specific band, the framework uses strict formal logic to assign hard verified or refuted verdicts. There's an amazing example from the validation tests. A conclusion had a super high AI belief score of 0.838. Most systems would just pass that right through, but the Lambda verifier flagged it as completely tainted because it caught a false premise down at the root level. It verifies the actual premise, not just whether the logic sounds consistent.
All right, Section 3, the irreducible error floor, the recurring villain.
Okay, here's where we meet the mathematical boundary of the whole explainer, the rho times p law. This law definitively proves that your error reduction is strictly bounded by how correlated your verifiers are. Think about it. If all your independent reasoning traces share the exact same fundamental misconception, like, say, a massive shared bias baked into their training data, you literally cannot fuse your way to the truth. If they all have the same blind spot, multiplying them just gives you a bigger blind spot. The source material puts this perfectly. Every honest safety or inference layer merely relocates a residual it cannot remove. It's literally like sweeping dust under a rug. The system can verify the structure of the logic perfectly, absolutely, but it cannot intrinsically know the universal truth of the external premises. Our sources actually measured this irreducible error floor, and it sits at exactly 0.012 for the trace bridge. That's the hard limit. And the wild thing is, this residual floor manifests absolutely everywhere across the architecture. In the trace bridge, as we said, it's that 0.012 floor. In standard AI distillation, it shows up as a massive 98% probability that a student model is just going to blindly inherit its teacher's errors. And incredibly, when we look at spatial projection, it even appears in physical hardware sensors, which is exactly what we're going to dive into right now.
Welcome to Section 4, Inverting Spatial Perception, Hardware Meets Software. All right, this is where a massive philosophical shift happens. We're taking this exact same predictive FGSGR framework and applying it directly to physical hardware. Traditional hardware relies on bottom-up polling. That means it takes in dense, noisy, continuous data from sensors, millions of pixels, radar pings, and it totally overwhelms the computer. The FGSGR framework flips this completely upside down. It uses a top-down generative projection. Using an inverse fast-Fourier transform router, it quite literally projects a 3D expectation of physical reality outward, and it only processes the residual error. It only looks at the tiny fraction of data that didn't match its prediction.
So, what does it do with that error? Well, the system filters that prediction error through a 5-state metacognitive grid. This step is absolutely crucial because it assigns a precision weight to the error. It asks, is the sensor experiencing a genuine environmental change, like a physical wall or obstacle, or is it just sitting in a super noisy environment, suffering from extreme signal jamming? This 5-state grid dynamically dampens the noise, which preserves the system's internal stability without crashing the hardware.
But remember our villain? Astonishingly, the exact same rho times p villain from the software side rears its head right here in the physical world. Testing revealed a crazy vulnerability. Slow, coherent adversarial poisoning, basically a tiny spatial frequency injected across the entire sensor field over time, could silently evade detection. It's the physical equivalent of poisoning a language model's premise. Now, the system does bound this using a sloop detector. That converts an unbounded vulnerability into a strictly rate-bounded one. But you guessed it, that irreducible residual still remains.
Which brings us to Section 5, Governing Aerospace and Swarms, the physical payoff. Because the system only processes prediction errors instead of raw data, it frees up a mind-bending amount of computational bandwidth. The real-world applications of FGSGR are just staggering. We are legitimately talking about cybernetic and aerospace capabilities that sound like they were ripped straight out of a sci-fi blockbuster. Let's look at a few of these in detail because they are so cool. First up, drone swarm robotics. Normally, you'd have to micromanage the exact X, Y, Z coordinates of millions of individual drones. A nightmare, right? Instead, this system projects a macro-level 3D harmonic wave. It's basically just imagining the intended geometric volume of the whole swarm. The cognitive architecture only steps in to process unpredicted anomalies, like a sudden burst of localized wind shear. The bandwidth savings here are just absolutely phenomenal.
Next, we have active acoustic camouflage. Think next-generation stealth for submersibles. The framework projects a constant expectation of the ambient acoustic background of the ocean. Then, the hull array actively generates the exact negative interference pattern needed to perfectly cancel out incoming active sonar or radar pings. It's not just absorbing sound, it's generative cloaking. It's like noise-canceling headphones, but for a nuclear submarine. And for the ultimate test of escalating physical stakes, deformable atmospheric re-entry shielding for spacecraft. As unpredictable aerodynamic heating creates localized extreme thermal spikes across a ship's hull, that spatial prediction error instantly triggers the reactive band. It literally reallocates magnetic plasma density directly to the exact coordinates of the thermal breach in real time. It is adapting to physical reality at the speed of computation. So what's the big picture? What you should really take away from this explainer is the sheer scale of this grand unification. Whether we are parsing a language model's text to hunt down illogical fallacies or dynamically protecting a spacecraft as it re-enters Earth's atmosphere, everything is beautifully unified under one single predictive paradigm: governed inference and the relentless minimization of prediction error. I'm going to leave you with this final, provocative thought directly from the source material. We have built an architecture that is exact where it counts. We can govern reality from code to orbit. But how much are we actually willing to build upon a foundation when we know the absolute mathematical limit of its truth? Because as we've seen today, no matter what you do, it's rho times p, all the way down. Thanks so much for joining me on this deep dive. Keep questioning those premises, and I'll see you next time.